Today we're going to start modern physics by looking at relativity. There are two big parts to modern physics, relativity and quantum mechanics. Both have been proven over and over again, but relativity and quantum mechanics are incompatible with each other. That is probably the biggest problem in physics today. So let's start with relativity. It's all relative. Here's a little demo. We have two videos of a man tossing a ball while another man pushes him. In the first video, the camera follows or moves with the man. In the second video, the camera is locked and the man moves with the frame. Another way to describe this is to say that in the first video is relative to the tosser, and the second video is relative to the observer. When we were relative to the tosser in the first video, this is the path that the ball followed. It's marked in blue dots, both up and down. When we were relative to the observer, this is the path the ball made. Again, marked off in blue dots. The path length is different in each case. Relative to the tosser, it's much shorter than when it's relative to the observer. Since the time for the ball up and down was the same in both situations, that's also going to change the velocity. Because remember, velocity is distance over time. If the distance is shorter relative to the tosser and longer relative to the observer, but the time is the same, the velocity is going to have to be change also. And that is relativity. Here's another example. It's similar to the demo, but a little different. As far as the hobo on the train is concerned, he's always moving at 1.2 meters per second, no matter what direction he's going in, whether he's going to the left or to the right. As far as the observer, the man standing by the side of the tracks, who sees the train moving at 15 meters per second to the right, the velocity of the hobo on the train is different, depending if the hobo is going right or left. If the hobo is going to the right, as is the case in this particular situation, then you can add his velocity, the 1.2 meters per second, and the train's velocity to get an overall velocity for the hobo of 16.2 meters per second. If the hobo is going to the left, and this situation, then we have to subtract the 1.2 meters per second from the 15 meters per second, and the hobo is going 13.8 meters per second. That's as far as the observer on the side is concerned. Here's another example. Let's say you have a gun, it fires a bullet, and the bullet's going 1,500 miles per hour. Let's put the gun on the jet and fire it. The jet is already going 500 miles per hour, and the bullet, remember, was going 1,500 miles per hour. So now the actual speed of the bullet is 2,000 miles per hour. That's relativity. That's relativity. But all this was known and accepted before modern times. What changed? Well, at the time, everyone thought that space was full of a luminiferous ether. They thought some kind of medium was necessary for the electromagnetic wave to move through, and they knew electromagnetic waves move through space, so they thought, okay, there must be a medium there, and they called it the luminiferous ether. Of course, we know now that electromagnetic waves don't require a medium at all, because the electric fields generate the magnetic fields, and then the magnetic fields generate electric fields, and so forth and so on in the process, which is called self-propagation. Michelson and Morley thought that they could detect the speed of the ether by measuring the speed of light in different directions, just like the hobo and the train we saw in the example. By the way, Michelson is the same Michelson who measured the speed of light on Mount Wilson, who we visited in an earlier lecture. In the central picture, you can see their experimental apparatus. Here it is as a line drawing, a little bit cleaned up, and here's a diagram of what happened. Okay, so light would leave the light source and go to the half-silvered mirror in the center. So light was going from here to this half-silvered mirror. When it hit the mirror, some would reflect off and go to this other mirror. Some would go through it to this mirror. Both of those waves would then reflect off the mirror, in this case going through it to this telescope, and in this case, this mirror reflecting off that half-silvered mirror and going this way, and they'd both wind up at the telescope. Michelson and Morley thought the beam's velocity would be different because of the velocity that they would gain or lose because of the ether. The difference in relativity would cause an interference pattern in the telescope. Michelson, here's what they thought the luminiferous ether would be doing, and depending on where the Earth was, they'd be going against it or towards it, depending on what time of the year it was. Here's an animation of what they thought would happen on the right. They thought the two beams would not reach the destination together because the ether would be interfering with one of them. That's not what happened. What happened is the animation on the left. There was no relative motion. Michelson and Morley thought they had failed. But as we've seen over and over again, sometimes failed experiments lead to more significant discoveries than experiments that turn out as planned. Not only did this experiment start to get people to doubt that there was an ether, no one today believes that there's such a thing, but it also proves that the light speed is constant and never relative. And that is a very important observation. That leads to special relativity. Special relativity was proposed in 1905 by a fellow named Albert Einstein. Special relativity has two postulates, or parts, if you'd like. One, all motion is relative. In a closed box, you can't tell if you're moving at a constant speed or standing still. And two, the speed of light in empty space will always have the same value regardless of the motion or the source of the observer. That, number two, is different than what we observed with the train or with the bullet and the jet. Let's look at each one of these two postulates separately. We'll start with the first one. Again, all motion is relative. In a closed box, you can't tell if you're moving at a constant speed or standing still. If you were on an airplane moving at a constant speed, you don't feel like it, even though you're moving 600 miles per hour. Obviously, these people don't feel like they're moving 600 miles per hour. They're serving food, they're taking food as if they were standing still. If you were drugged and put in a crate, would you be able to tell if you were in a cargo hold of an airplane or sitting on the ground? The answer is no. The second postulate, the speed of light in empty space will always have the same value regardless of the motion of the source or the motion of the observer. That was proven by Michelson and Worley. In other words, it doesn't matter if you're moving or not. Relative to the light will always be moving at the same speed. So even though the man on the left is moving, he's going to measure the light at the same speed as the man standing still on the right. Let's go back to the jet again. If the jet's not moving, in the top picture it's not moving, and a light comes off of its wing, that light is moving 186,000 miles per second. If the jet is moving 500 miles per hour, the light is still moving at 186,000 miles per second. This leads to some very interesting effects that are kind of out of our normal experience. Remember, this goes back to our original demo. If we measure the ball moving at different speeds relative to who we were relative to. In this example, instead of a ball, we have a flashlight. The light travels different paths depending on who it's relative to, just like the tennis ball in the original demo. To the man who's holding the flashlight in the very top spaceship, the light goes up to a mirror, hits the mirror, and then back down to a detector. But to an observer who sees both the flashlight and the moving spaceship, sees the light travel at a different path because the spaceship is moving, the mirror is moving, the detector is moving, so the path it's going to follow is that one. In our demo, we determined the speed of the tennis ball was relative to the observer, but not in this case because light can only have one speed. Well, if the speed of light is constant and the path is longer, there's only one other thing that we can change here, and that's time. And that's exactly what happens. If you are in motion, your time will slow down. This is referred to as time dilation. And this is probably one of the weirdest things about relativity. Here's a video.
$0.3 million at $2,300,000.
In 1971, Joe Haefele and Richard Keating put the theory to the test. They flew 4 atomic clocks around the world to compare the passage of time on an airplane with time on the ground.
I don't trust these professors who get up and scribble in front of blackboards claiming they understand it all, because I've made too many measurements where they don't come up with the numbers they say.
Richard had told me that in all the previous work he had done, he had never seen the effect of time dilatation.
I hadn't.
Had never seen it.
I knew what was being predicted and that, but it always seemed to me that the best proof is to measure it.
Well, hopefully it's going to be available for 1 minute.
To see how time slows down with speed, they had to fly all the way around the world in the original experiment. Today's atomic clocks are more accurate, so the warping of time should be apparent even on an ordinary transatlantic flight.
Champagne for you, sir? Yes, one for me and one for my friend.
Certainly. About 5 minutes past 4 local time, which is 5 minutes past 9 English time.
Einstein said time is that which is indicated by clock. I think I know what a clock is, therefore I think I know what time is.
Seem to be following an unbelievably constant track.
En route, they collected data from the pilot, then put it into Einstein's equations to predict the time change.
We have accumulated so far a change of 34 nanoseconds. Broadly speaking, it seems to confirm the original prediction. The clock will have gained somewhere between 37 and 40 nanoseconds when we land in about half an hour's time.
Suppose you would live for 100 years and you would spend your entire life on one of these aircraft flying around the world. You could expect to be younger than people who did not do that by about 1/10,000th of a second.
The UTC, USNO master clock,
To measure exactly how much time changed relative to time on Earth, the clock on the airplane had been synchronized with the international standard at the start of the trip. Then it was compared to the same standard when it landed in the United States.
If we put other cables in here, that changes by about...
The clock on the plane disagreed with the ones on the ground by 40 billionths of a second, just as Einstein predicted.
The difference can be calculatable. Here's the equation. It's not a very difficult equation. Here it is. This leads to the famous twins paradox. Take two twins. One goes off and back in a spaceship, moving it at some large fraction of the speed of light in the top picture. When the twins return, the twin in space will have just aged slightly, while the twin left behind on Earth will have aged a lot. Here's a video explaining that.
One of the towering great achievements of the human mind and our understanding of the universe is Einstein's theories of relativity. It's actually, the tenets of it are quite simple, almost scary simple. It makes only two assumptions: that the speed of light in a vacuum is constant no matter who is doing the measurement and no matter what direction you are moving or how fast. You'll always get the same measurement for the speed of light. That's assumption one, which, by the way, experiment has shown to be true. Assumption two, that the laws of physics as you measure them are the same for every observer who would be doing the measuring, provided you are on a vessel that's either moving at a constant speed or not moving at all. Those are the only two tenets that you have to buy into. And all experiments have shown that both of those two tenets are correct. Given those two tenets, extraordinary, spooky phenomenon derive from them. For example, as you travel faster, or if you find yourself in the vicinity of a higher source of gravity, time ticks more slowly for you than it does for other people who are not. It's not just your clock, it's everything about you and your environment slows down. You don't notice this because everything is slowing down, including your neurosynaptic thought rate. So it goes unnoticed to you, but it's patently obvious to everybody else observing you. And this leads us to the famous twin paradox. So here's how it works. Let me get a pair of twins, all right? They're born the same time, they're the same age. And now one of them I will send off at 90% the speed of light. And the other I'll keep down here on Earth. So we can ask, how do their aging rates compare? Okay? Turns out, this twin that I've already sent, his clock ticks 44% as fast as this twin's clock, our clock here on Earth. So, this twin is aging more slowly than this one. That's at 90% the speed of light. Let's pump it up some more. How about 99% the speed of light? Now the time ticks at only 14% the rate, as it does back here on Earth. How about 99.9%? We're getting closer and closer to the speed of light itself. And at that speed, the clock ticks only 4.5% as fast. So, what does this mean? Tell you what it means. This twin that traveled for 5 years and comes back, if they went at 99.9% the speed of light, after 5 years, they're 5 years older. We have aged 110 years. It's called the twin paradox. It's only a paradox if you think about it in sort of classical terms. How could that be? But in relativity, there is no paradox at all. That is a fundamental feature of what happens when all you do is presume that the speed of light is the same for everybody and the laws of physics remain constant.
Does this affect us on a daily basis? Yes, it affects our GPS, or Global Positioning System. GPS lets us find a position anywhere on the planet. It's how your phone can show you a map and know where you are. This is through an array of satellites in orbit, moving at high speeds. Because they are moving at such high speeds, their clocks must be adjusted to compensate for the time dilation that they would be experiencing. We'll see some more on this later. Besides time being affected, length is also affected. Length of things moving at a high rate of speed is contracted or shortened. And that can be calculated. Here's the calculation for that. Mass is also affected. Things get more massive, and that can also be calculated. Here's a table showing how mass increases. You can see this is the right column over here is a percentage of the speed of light, and this is your multiple of how much your mass would increase. Notice by the time you get to 99.99% the speed of light, your mass is increased by 22.4 times. Imagine. We actually do such things in particle accelerators, and we'll get to that on another day. Another result of special relativity is the mass-energy equivalency. That is, mass is energy and energy is mass. We have already studied this in the past when we were looking at energy.
It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Cockcroft and Walton in 1932 experimentally.
That was special relativity. 10 years after that, Einstein incorporated gravity with special relativity and came up with general relativity. Here's an illustration of that. As part of general relativity, he came up with the idea of space-time, wherein he combined the three dimensions of space with time. Einstein also established the equivalency principle. In a closed box, you can't tell if you're accelerating through space or you're being pulled down by the gravity of Earth. Or there is no difference between gravitational mass and inertial mass. This is why we always define mass as being both the amount of a substance of an object and a measure of that object's inertia. Well, if that's true, and it is, if you're accelerating through space, if light enters a peephole on one side of your ship and the ship is moving, the light would shine on a spot on the other side of the ship lower than the peephole because the ship is moving forward, right? As if the light curved downwards. Well, Einstein reasoned then, by the equivalency principle, the same thing would happen due to gravity. So gravity, which is a mass curving space-time, would cause the light to curve around that curve or to bend. And this was actually observed, and it was the first proof of Einstein's theory. At night we can see and map all of the stars in the sky on the left of this illustration. If we wait for a solar eclipse, when the sun is blocked out by the moon, we can see the same stars during the day. Otherwise, we wouldn't be able to because the sun is too bright, and we wouldn't be able to see where any of them. And that was done during a solar eclipse, and the stars appeared to be in the wrong place because the light was bent because it was following the curve of space-time caused by the sun. Astronomers have found many examples of this phenomenon, which is called gravitational lensing, where the light from some distant object is bent around a massive object between the Earth and that distant object. In this illustration, the Earth is down here. There's a massive galaxy here, and then there's another galaxy here. Well, the light from the galaxy on the upper left gets bent around the curve created in space-time created by the middle galaxy. And so from Earth, we wind up seeing different images of that same galaxy. We see multiple images of the back galaxy because of the curvature of space. Here's an actual illustration of galaxies whose images repeat in the sky because they're curving around something between us, the Earth that is, and that distance object. But remember, it's not just space, it's space-time that's being bent. So not only are dimensions being bent, time is being bent. Time is affected the same way. It's by massive objects. Not only are massive objects bending space, they're also bending time. The more massive an object, the more space and time bend around it. Black holes, which are actually collapsed massive stars, are the most massive single objects we know of. Time slows down a lot. If you fall into a black hole, time would seem normal to you, but if we were able to watch you fall in, you would appear to be moving very, very slowly. We would not be able to watch you, of course, because once you've gone past something called the event horizon, light bends so much around this black hole that it can't even escape from it. That's why we call it a black hole. This is a picture of the massive black hole at the center of our galaxy. Now that we've learned about time slowing down, if you're moving, and slowing down when you get close to a large mass. What does that mean for our GPS system?
It's a navigational tool used by millions of people every day. With it, drivers know where they're going. Pilots fly planes more safely. It helps construction workers build straighter roads. Farmers plant fields more efficiently. Because of it, golfers choose better clubs. Skiers find faster ways down mountains. The uses for this innovative tool are virtually unlimited. It's called the Global Positioning System, better known as GPS.
So, exactly how does this incredible tool work?
So imagine you're on a field and you wanted to triangulate where you were because you know the positions of things in the distance that you can see. By measuring the direction to one object and another object, you can figure out where you would have to be in the field. Well, GPS is like that, but it's larger. It's in all three dimensions, not only where in the field, but how high, and also it's measuring time. You have 4 satellites. They're sending you signals, and you're measuring accurately where the satellite appears to be and when the signals are sent. And from that, you can figure out where you are on the Earth's surface.
The Global Positioning System is a network of over 30 satellites orbiting 20,000 kilometers above us. They move at a speed of 14,000 kilometers per hour. Each satellite follows one of 6 orbits, arranged so at least 4 satellites are visible from any point on Earth. The satellites constantly transmit signals, easily picked up by anyone with a GPS receiver. Each signal contains information on where the satellite is and what time the signal was sent. Using this information, the receiver calculates its distance from the satellite. This is done by multiplying the signal speed, the speed of light, by the time the signal travelled. The receiver then repeats this procedure for 3 more satellites, narrowing down its location to within a few meters.
To achieve this incredible accuracy, the timing information from the satellites must be extremely precise. So inside each GPS satellite is an atomic clock, the most accurate timing device ever created.
The GPS is so precise, it must take into account a number of subtle effects. Some of these are predicted by Einstein's theory of relativity, an idea that revolutionized our understanding of the universe. This theory includes special relativity and general relativity. Special relativity is a theory of space, time, and motion. Key to it is the fact that motion alters time. We see time running slower for a clock that's moving relative to us. Satellite-based GPS clocks are moving past us at 14,000 kilometers per hour. Because of special relativity, they gradually fall behind clocks in Earth-based receivers at a rate of 7 microseconds per day.
After Einstein formulated the theory of special relativity, he went further ahead and he proposed his theory of general relativity, which is not only a theory of space-time, but it's a gravitation theory.
Key to Einstein's theory of general relativity is the fact that gravity alters time. Clocks farther away from Earth, where gravity is weaker, run faster than clocks closer to Earth, where gravity is stronger. The GPS satellites are located 20,000 kilometers above Earth, where gravity is much weaker than on the surface. Due to general relativity, satellite clocks run 45 microseconds faster daily. When we combine the effects of special and general relativity, satellite clocks run 38 microseconds fast every day. This may not seem like much, but if uncorrected, all GPS measurements would be off by 11 kilometers daily.
The effects of relativity on Earth are normally 1 part in 10 billion, and so that's an incredibly small effect, and you're used to thinking you can forget it for most things. But when you're relying on how far light travels in a particular amount of time, if you're wrong by even microseconds, then the distances that you're getting wrong are that much larger.
To correct this error, engineers adjusted the atomic clocks inside the satellites, so on Earth they ran slow by 38 microseconds per day. This compensated for the effects of relativity and meant that, once in orbit, the clocks ran accurately, giving us the powerful tool we have today. So, as you see, what began as an abstract theory over 100 years ago is now used in everyday technology. Every time you use GPS, you're using relativity. Whether you're heading out to meet friends, trying to find the nearest movie theatre, or looking for a restaurant in another country, you'll always know where to go using GPS.
So relativity is not just something to study in school. It actually affects daily events in people's lives. Your life.